In this video, we're going to focus on electronic configuration, and this is part 2 of atomic structure. So electronic configuration is basically the arrangement of electrons in shells, and we need to follow a principle by which we are going to arrange different electrons in different shells. Right, so the first shell can hold maximum of 2 electrons, second shell can hold maximum of 8 electrons, and third shell can hold maximum of 8, and the last one can hold maximum 2 electrons. And this is only applicable for the first 20 elements, right, which we'll be focusing on in this video. Let's take an example. For example, we have sodium. Right, the first thing you need to do is reduce the number of electrons. The number written on the top is going to be the atomic number, and the number mentioned below is atomic mass. Right, and we know that atomic number is the number of protons and atomic mass is the sum of protons plus neutrons. Right, so in sodium atom, the number of protons and electrons is equal because it is not having any kind of charge, so we can assume it is having 11 electrons. So first shell can hold maximum 2, second can hold maximum 8, and last can hold maximum 1 electron. Right, now if you draw the structure of sodium atom, you need to draw it like this. You need to write the sodium in the center. You'll be having the first shell, the second shell, and the last shell. Now staying to the rule, the first shell can have maximum of 2 electrons. Let's draw 2 electrons. Second shell can have maximum of 8 electrons, 1 2 3 4 5 6 7 and 8, and last shell can have maximum of 1 electron. Right, so let's take another example. For example, you need to draw the structure of nitrogen. Right, now in nitrogen there are 7 electrons, so we need to write the electronic configuration for 7 electrons. So first shell can hold maximum 2, and second shell can hold maximum of 5 electrons. We have nitrogen, we have the first shell, and we have the second shell. The first shell can hold maximum 2 electrons, so electrons can be represented with the dot or with the cross. Right, so here we have another example. Let's say oxygen. Right, so let's draw the structure of the oxygen. We have 8 and 16, so it has 8 electrons. Let's arrange these electrons in the shells. First shell can have maximum 2, and second can have maximum of 6 electrons. So here we have the oxygen atom. We have the first shell, and we have the second shell. First shell can have maximum 2. Let's draw 2 electrons, and second can have maximum of 6 electrons, 4 5 and 6. Right, in some cases you will be given different ions and you are required to draw the electronic configuration of different ions. Okay, so how do we draw electronic configuration for the ions? Let's say sodium ion. Right, you will see that there is +1 charge on the sodium ion. It means that the number of electrons and protons are not equal. It will be having 11 protons, as you can see, 11, which is the atomic number of sodium. And for number of neutrons, you need to subtract from the atomic mass. That will be 12. And for electrons, you see, since there is a +1 charge, it means it has donated 1 electron. Right, so that will be having 10 electrons. So let's draw the structure of the sodium ion. We have sodium in the center, and we have to arrange these 10 electrons. Like first shell can have 2, and second can have maximum of 8. So ions have completely filled outermost shell. Okay, so we have the first shell, and we have the second shell. First shell can have maximum 2, and second can have maximum of 8 electrons. Right, and since it is having a positive charge, so you need to draw +1 on the bracket. Right, and since the positive ions are called cations, so this is a cation, and you represented, this is sodium +1 with 11 23. Let's take another example. For example, we have nitrogen, for instance, and this ion with a negative charge is called as nitride ion. Okay, so 7 and 14. So let's reduce the subatomic particles first. The number of protons is going to be 7, neutrons is going to be 14 minus 7, and electrons is going to be, since this -3 means it has gained 3 electrons. Right, so that will be 10. So let's draw the structure of this ion. We have nitrogen, we have the first shell, right, with the 2 electrons, and we have the second shell with the 8 electrons. and it will be having a -3 charge. right? In some cases, you need to represent the electrons which are gained or lost with a different structure. For example, you need to represent these 3 electrons with a dot, right? Because these are the electrons which it has gained. Okay, so try this question by yourself. We have oxygen. So go ahead and try this question. You can pause the video and try this question. So we have the number of protons, 8, neutrons, 8, and electrons, 8 and 2, 10. Let's arrange the electrons. First shell can have 2, second can have 8. So let's draw the structure. We have oxygen. First shell have 2 electrons, and second shell has 8 electrons. And it will be having a charge of -2, right? And you can also represent the electrons which are gained with the dots, right? So this is about the electronic configuration, and this is how you draw the electronic configuration of different atoms and different ions, right? The next part we are going to focus in this video is isotopes. This video is going to be very comprehensive. As per your request, I'm keeping it as short as possible. So isotopes. Isotopes are the atoms of element which have same atomic number but different atomic masses. So let's take an example of carbon here. And carbon has 3 isotopes, as you can see. They are the atoms of same element, with same atomic number, but with different atomic mass, right? We can also tell, let's reduce the subatomic particles first of all, and then we can conclude one more thing about the isotopes. If we reduce the subatomic particles, the protons are going to stay 6, 6 here, and 6 here, right? So protons are going to stay same. Let's just reduce the neutrons. So we have 12 minus 6, 6, 7 here, and 8 here, right? And let's just reduce the number of electrons, 6 here, 6 here, and 6 here. So you will notice that they are having the different number of neutrons, but number of protons are same in them. Right? So we can also say that isotopes have same number of protons and electrons. So they have the same number of protons and electrons, but they have different number of neutrons. Right? This is another way to describe or define isotopes, that the number of the protons and electrons are going to stay same in them, but the number of neutrons are different, right? So if we look at the electronic configuration of isotopes, that is going to stay same, right? That is going to be 2 and 4. So they have same electronic configuration, right? And they have same number of valence shell electrons, right? So same valence shell electrons, which means that they have similar chemical properties. So they have similar chemical properties, right? So please be reminded, in exam you may see a question that why do isotopes have same chemical properties? The reason is that they have same number of valence shell electron and same electronic configuration, right? So they have similar chemical properties. Let's have a look at some questions from the past exam. The question is about go ahead and try this question. You can pause the video and try this question by yourself, right? The question is about sulfur and compounds of sulfur. It has several isotopes. Define the term isotope. So we know that atoms of same element, right, having same number of electrons and protons, okay, but different number of neutrons. Right? Let's go with the B part. Reduce the number of protons, neutrons, and electrons in the sulfidine. So they've given us sulfidine, and number of protons is going to stay same. That is 16. So proton number is given at the bottom in this question, right? So always be reminded that the smaller number is going to be your proton number, right? So 16 neutrons, you need to subtract 36 minus 16, that will be 20. And electrons, since you see there's a -2 charge, means it has gained 2 electrons. So that will be 18, right? What if they ask you to draw the structure of this ion? How will you draw? Sulfur, we have the first shell. So let's arrange first of all like 2, 8 and 8, right? 18. So we have the first shell. We have the second shell with the 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And we have the last shell with the 8 electrons, right? 1, 2, 3, 4, 5, 6, 7 and 8. And as a reminder, make sure you write down the charge on the bracket, since this is anion. And anions are negatively charged particles, right? So we call them anions. Let's move on to third content which we're going to focus in this video. That is how to calculate the relative atomic mass from the given isotopic abundance. In some cases, examiner is going to give you the relative atomic, the isotopic abundance of different isotopes, the percentage abundance, that how abundant they are in nature, and will ask you to calculate the relative atomic mass from the given data, right? Let's have a look at this question. Lithium has 2 naturally occurring isotopes. One is lithium-6 and one is lithium-7. Okay, and the table below shows the relative abundance of these isotopes. Like lithium-6 is 10% and lithium-7 is 90%. So actually it's very simple. Just you need to transform this data into a mathematical expression. That will be 10% of 6, and you have to add, that will be 90% of 7. Okay, for lithium, right? So 10% of 6, 10 over 100 into 6 plus 90 over 100 into 7, right? So if you simplify this, you'll be getting 0.1 times 6 plus 0.9 times 7. You'll be getting 6.9 as a relative abundance. So go ahead and try this question by yourself. Question number 2. Chlorine has 2 naturally occurring isotopes. One is chlorine 35 and its relative abundance is 75%. And the second isotope is chlorine 37, which has a relative abundance of 25%. So go ahead and try this question. You can pause the video and try it by yourself. So for this question, what you need to do, simply transform this data into mathematical expression. 75% of 35, then add plus 25% of 37. 75 over 100 times 35 plus 25 over 100 times 37. So that will be 0.75 times 35 plus 0.25 times 37. So if you simplify this, you will get 35.5 as the relative atomic mass of chlorine. Okay, so this is the relative atomic mass of chlorine. Thank you very much. Stay tuned for the next videos.